And let's see what we can do with this equation so far. Let us solve them for the idealized case of a star of constant density. The case is artificial, but some order of magnitude insight will be obtained from it. So we have the mass continuity equation and the equation of hydrostatic equilibrium. If the density is constant, then we can replace the density by 3 times the mass over 4 pi times the cube of the radius. Now let's give this mass here in the hydrostatic equilibrium and on the mass continuity equation the subscript little r to distinguish between the mass in a shell and the mass of the whole star. Now the mass in a shell is the integral up to that shell, and if you substitute here the density, then this is going to be little r cubed to big R cubed times the mass. Again, little r is the density inside the star, and r is the radius of the whole star. So we can use this definition of the mass in the shell to substitute in the equation of hydrostatic equilibrium. We have the PdR then is equal to minus G times big M times the density times little r to the over R cubed, dr. And now we can also use the mass continuity equation to replace dr by dm. If we use the continuity equation to say that dmr is equal to 4 pi r square rho dr, then we can write the pressure equation as dp is equal to minus gm rho over r3 times r dr, and replace here dr by dm over 4 pi r square rho, and we can eliminate rho from this equation. What we have then is dp is equal to minus gm to the power of 4/3 over 4 pi r4 over 1 over the mass of the shell to the power of 1/3 dmr. Now everything that is on here is a constant. So if you want to integrate the pressure, we simply need to integrate in mass. If we integrate it from the core to the surface, so from 0 to r, if we integrate from the core to the surface, then we find that at the surface, the pressure is 0. And at the core, let's call it central pressure, PC, then it's going to be gm 4/3, 4 pi r to the 4th. And now the integral mass is going from 0, which is the mass at the core, there's nothing, to the mass of the star, which is what you would have at the surface. Solving this, you find the central pressure in the core to be 3 times gm squared over 8 pi r to the 4th power. So this is the expression for the pressure in the core under the approximation of constant density. Substituting the constants, we can find a numerical value for it. This is going to be then pressure is about 1.34 times 10 to the 15 some squared to the 4th power of the radius divided by the radius of the sun in CGS units, which is dyne over centimeter squared. Now, if you convert this to atmosphere, an atmosphere is 1 bar, that gives you about 10 to the 9 in the same scaling with mass and radius. So the pressure in the core of the sun is about 1 billion atmospheres. Now we can substitute on this the equation of state. The equation of state, the pressure is the heat capacity constant volume times the density times the temperature. If we substitute for the pressure at the core and have constant density, then we're going to find the temperature at the core. If you substitute these values, you find that the temperature of the core is of the order of 10 to the 7. And again, the scalings are going to be mass squared, the radius to the -1 Kelvin. So this should be the order of magnitude of the temperature of the solar core. We found pressures of the order of billion atmospheres and temperatures of the order of 10 to the 7 Kelvin. Indeed, the temperature in the core of the sun is about 15 million Kelvin. And indeed, back in module 5, we highlighted that the presence of absorption lines in the solar spectrum shows that the sun is a case of Kirchhoff's third law, where the atmosphere is colder gas superimposed on a hotter lamp. What we just found that the temperature of the core is of the order of 10 million Kelvin shows just how much hotter this lamp is. The atmosphere of the sun at 6,000 Kelvin is indeed a much colder gas in comparison to the very hot gas at the solar core.